reaction, right? That's a combustion reaction and a synthesis reaction. But really, that experiment is more focused on single replacement reaction. Excellent.
One of the questions, if you have to answer all the questions across the hard sheet.
What was one of the questions?
What happened with the was came in, or is that pop?
That's more the pop that I'm looking for, okay? The pop is the sound that the it's a reaction that's occurring. It's the sound of that hydrogen expanding real quick as it reacts with the oxygen. It's like thunder, basically. Like, it creates that energy given off like that makes the sound. No. Mostly the pop is a test for hydrogen gas. Okay? So what we're doing there is that we know that we started off with zinc. This is lab stuff, but that's okay. We know we started off with zinc and hydrochloric acid. Okay? And then the popping noise indicates that hydrogen was there by itself. So then knowing the pattern, we then have to go, okay, well that means that we must end up with zinc chloride. That must be the other one because of the single replacement. So the popping noise is more of the test for hydrogen, which then indicates, okay, hydrogen by itself now, it used to be joined with chlorine, so that means single replacement reaction must have occurred. What's going to happen?
What would be an example for an endothermy?
The little ice pack thing that's in a first aid kit, but to get that started, right, first you have to pop the bubble. That just gets those things together. But then what does it tell you to do after you pop the bubble? You shake it, right? So here's who asked the question about is it always heat, okay? Shaking, right? That's giving that little oomph to make it go. Will it go on its own if we just sort of sit them together? Yeah, but the shaking makes it happen a little faster. Does that make sense? Amy, go ahead.
This kind of has to go back into the lab.
Okay.
So, like, we're saying, we have to say, like, what evidence that chemical reaction occurred.
Okay.
So, say, like, that's one of them, like, make a popping noise if you know this gas.
Technically, that's a separate chemical reaction.
Yeah.
That's a chemical reaction between hydrogen and oxygen. But the chemical reaction that you were technically observing was the reaction between the zinc and the hydrochloric acid.
So should we include that or no?
You can, at least definitely in the observation section, okay? When you're talking about your conclusion, you can say that it happened, but like I said, that popping noise is more of a test for hydrogen. So that's more proving that this happened here.
Yeah.
Does that make sense? I'm not so worried about the reaction with the hydrogen and the oxygen. That pop is, yeah, it's more of a test for the products of the single replacement reaction.
Okay.
Good there? All right. The next picture, the next set of pictures, it doesn't show up, they didn't copy the best on yours there, okay? Some of them copied well, some of them didn't, okay? But if we look for generalities, okay? First, if we're looking to categorize the reaction as endothermic or exothermic, if it's endothermic, where should the energy of the products be versus the energy of the reactants? Higher. So we should see some kind of an uphill climb, like this one right here, which I think copied pretty good. I think it's the second one there. Okay.
No.
Third one. Oh, the third one copied better. Sorry. So endothermic reaction here, right? Endothermic reaction here. This is the first one. Okay. Notice, and this is going to be more important for the second question. Notice, look at how big of a jump there is from here to here versus here to here. Does that make sense? Okay. This is a big step from reactants to products. This is just a little step from reactants to products. Okay? Same thing with the exothermic ones. Here's a big drop from reactants to products. Here's not such a big drop from reactants to products. Yes, sir.
So, the first one,
Yep.
it's absorbing a lot of it.
Yep.
Reaction that doesn't really just happen.
Right. So it's now this is an endothermic reaction first, right? Because our products end up with more energy than started with, right? But if you look at the change in energy, right, how, like you said, how much energy has this, and really here we're just looking at beginning and end, right? How much energy has this gained from here to here? A lot or a little? A lot, right? But then from here to here, not very much, right? So what would we say about stability here? Which of the products is more stable? This reaction or this reaction? 1 or 2? 2, because it hasn't gained as much energy, right? Okay. On the other hand, with the exothermic reactions, right? If we look, let's say like these two here, number 3 and number 5. Reactants both start higher than products, okay? But look at how big of a drop there is from reactants to products in number 3 versus reactants to products in number 5, right? Bigger jump, or a bigger drop from here to here, right? So what does that say about the stability of the product in number 3 versus number 5? It's more stable.
Wait,
3 is more stable than 5. Okay? Because it's not necessarily, no. We're looking at where we start versus where we finish, right? Reactants, products, okay? So if we look, reactants start way up here from an energy standpoint, but they end up way down here from a product standpoint. So if we look at how much energy was lost here, it's kind of a lot of energy, right?
Right.
Here, right, reactants start a little lower, which means they're kind of more stable to begin with, right?
Yeah.
Products end up in, I don't know, let's say it's approximately the same amount of energy, okay? When we're looking at stability, it's the amount of energy that we lose, or how much lower we are than where we started. So this one's going to be a more stable product, just because it gave up more energy than it started with. Does that make sense? Yeah. So we're looking at jumps there. Yes, Rob? Now, an endothermic, right, we're putting energy into. Is that a good thing? Generally, we said, what are things looking to do out there in nature? Lose energy, right? So yeah, this situation here, this is going to be much more likely to happen because of the fact that there's not as big of a jump there. Okay? Yeah. The fourth one is a little hard to tell because like it's not exactly with the other ones. Although this is going to be a much more stable product because it is drop, okay? But if you look at where its energy is, like on the y-axis, versus where like this one's energy is, okay? This product is more stable than the reactants, definitely. But if you look in the grand scheme of things, this product is not the most stable product that we've made in any of those reactions. Morgan, go ahead. Yes, although if we're looking at where they start versus where they finish, that will sort of give us indicators of, is this likely to happen? If there's a big drop, then yeah, it's pretty likely to happen because those products have less energy than the reactants. If it's not such a big drop, it's not real big advantage going from those reactants to those products. Okay? So that should help you answer letter B. Craft that into some kind of a written response there for letter B. Okay? And if you've made some notes on your graph, that's fine too. Yeah. Right, because right, yes. They are different, right? We're talking about gaining versus losing energy, so there should be some differences. And so if you made some notes there within the graphs, then that's okay too. Yes, son.
Are exothermic reactions like automatically going to be more stable than endothermic?
Generally, yeah. Although, like we kind of mentioned before, there are some other factors that go into that. So I can't say absolutely yes, exothermic are always more stable than endothermic because there's other factors that go into it. All right, good there. Yeah. Peter's good. He's all right. So let's talk a little bit about reaction rates. Okay. When we talk about reaction rate, we're talking about how fast does this occur? How fast is this chemical change occurring? And we'll see here that there are some physical things we can do, and then there are some chemical things that we can do. First, what are some physical things that we can do to make a reaction happen quicker? Okay? Temperature is definitely one of them, all right? What are some other things that we can do? Surface area. Oh, they're all listed there for you. All right, let's go here. Temperature, right? First, generally reactions go faster at higher temperatures. It should say faster, not necessarily fast. Fast. So generally, reactions go faster at higher temperatures. Why are reactions going faster at higher temperatures generally? Good. They're moving faster, right? And generally, in order for a reaction to occur, things got to run into each other or be close to one another. So that increased speed of particles as we increase the temperature generally results in a faster reaction. Good. Good. Sorry. I ran out this morning. Next, surface area. Oh, wait, before we go surface area. We said that reactions generally go faster at a higher temperature because what are the particles doing more? Moving, right? Can we do something artificially to make that happen? Yes.
Yes. No, I'm saying
Say again? Well, once burner is doing the temperature, right? What about artificially making them go faster? Not quite, but I think you're getting where I want to go. What? Not compressing them, that's something different. Shaking them or stirring them, right? Shaking and stirring are basically just artificial temperature increases, right? Okay? Say again? Yeah, it's like the ice pack thing, right? That, we're making those things go faster. And it's kind of weird because higher temperature, but the ice pack is lower, right? Really what we're doing is we're making those molecules or particles come in contact with each other faster, and that's going to cause the reaction to go faster. Next, surface area, right? Large surface area for the reactants is going to speed up the reaction. Say again?
why wouldn't it be like a small effect closer together?
But now, when we talk about surface area, right, that's the part that's in contact with other things, okay? For example, think of making lemonade or think of making Kool-Aid or dissolving sugar in water, right? Is it easier to dissolve sugar that's granulated or sugar cubes? Granulated sugar. Why? Because what is there more of there? Well, it's the same number of particles, but how many of them are touching the water that they need to mix into? More of them, right? So that surface area increases the opportunity for those particles to react with other stuff. Okay? Good there? And then concentration. Okay? Generally, what's going to make a reaction go faster? More stuff, right? Concentrated solutions react faster. If you increase the concentration of the reactants, if you put more of them there, generally things will go faster. Right? Why do you think I gave you 6 molar hydrochloric acid in the lab the other day? Even though it's kind of dangerous, 6 molar is a pretty high concentration. As soon as you squirted the hydrochloric acid in with the zinc, what started happening? Bubbles like almost immediately. Okay? That also holds true for gases. Gases at higher pressures will react faster. What did we say that pressure related to? Do we remember? Not necessarily movement of particles.